as a whole, but rather that a new generation began to discover phenomena that, quite simply, protons, neutrons, and electrons could not explain. The longer scientists looked into the matter, the clearer it became. The number of elementary particles was not 3, but more, many, many more. And they could be produced and measured and studied in the great accelerators that, like this one, have become the tools and the monuments of modern physics. And as the number of known elementary particles increased, seemingly without limit, so did the need to organize what was known about them, to find patterns among their properties. In other words, what was needed was nothing less than a new kind of periodic table. But this one would be a periodic table not of atoms, but of the inner constituents of atoms. The neutron and the proton are close relatives of one another, and they belong to a larger family of 8 particles with similar properties. And each of those particles has an antiparticle with the same mass but opposite charge. Furthermore, for each particle and each antiparticle, there's another with similar properties but higher mass. And for each of those, yet another with still higher mass, and so on. So while one group of scientists, the experimentalists, labored at the great accelerators to find evidence of new elementary particles in the debris of collisions between the old ones, other scientists, the theorists, worked equally hard to find order in the increasing complexity and proliferation of particles. And in a striking example of history repeating itself, it was found that the patterns of the elementary particles, like the periodic table of the elements, could be explained if the particles, like the atoms themselves, had internal constituents, and like the constituents of the atom, there were 3 in number. They were called quarks. For example, each member of the family containing the neutron and proton is made up of red shapes represent up quarks and have positive electric charge of 2/3, while the 2 kinds of smaller blue ones are called down quarks and strange quarks, 1/3 of the elementary unit of charge. They combine together so that +1 times the charge of an electron. Each quark also has spin, and they add together to give each particle as much quantum spin as an electron. The more massive particles, remember in modern physics more mass means more energy, have the same sets of quarks, but they're also in orbit, accounting for the extra energy. And so it goes, for this family and others. Elementary particles composed of even more elementary particles in combinations of quantum states. Like the proton, neutron, and electron, the 3 kinds of quarks called up, down, and strange may be only another chapter in the saga of atomic structure. Already, 3 more have been postulated. The latest are called charm, top, and bottom. And each of these types has an antiquark. Do they all really exist? With a brilliant model, a bit of luck, and a very big machine, perhaps they can be found just around the corner.